Your air conditioner does not cool your house. I need you to sit with that sentence for a moment before I explain it. Your air conditioner does not cool your house. It moves heat from inside to outside using a compressor, a refrigerant, and enough electricity to light a small town. It is a heat pump running in reverse, and it is the single most expensive appliance in your home by a factor of 3. The average American household spends $2,000 to $2,500 per year on electricity. Air conditioning accounts for roughly 50% of that bill during summer months. In the Sunbelt states, that number climbs to 70%. You are spending $1,000 or more per year to run a machine that was invented in 1902 by a man who was not even trying to cool a building. He was trying to control humidity in a printing press. Meanwhile, there is a cooling device that requires no compressor, no refrigerant, no chemical coolant, and no specialized equipment. It can be built in under 30 minutes from a bucket, a fan, and water. It uses 75% less electricity than a window air conditioner. It drops room temperature by 10 to 20 degrees Fahrenheit in dry climates. It has been in continuous use by human civilizations for over 4,500 years. And the HVAC industry has spent the better part of a century making sure you believe it is primitive, unreliable, and beneath the standard of a modern American household. The device is called an evaporative cooler. Its common name is a swamp cooler, and the principle it operates on is so fundamental to physics that your own body uses it every time you sweat. Welcome to Camping Secrets. If these stories matter to you, the subscribe button and the bell are the best way to make sure this knowledge survives. This is where we dig up what the industry buried. Now let me take you back 4,500 years. Because this is not a modern invention. It is one of the oldest engineered systems in human history, and the civilizations that built it did not have electricity, refrigerant, or a monthly utility bill. Wall paintings dating to approximately 2500 BC depict Egyptian servants fanning air across clay vessels filled with cold Nile water to cool the chambers of royalty. But the Egyptians did not stop at wet pots and reed fans. They engineered it into architecture. They hung soaked reed mats over doorways and windows so that every breeze entering the home passed through wet fiber and arrived inside measurably cooler. This was not folk wisdom. This was applied thermodynamics built into the infrastructure of an empire. The Persians took it further. They constructed wind catchers, tall chimney-like towers called badgers that rose above the roofline and caught prevailing winds at elevation. The captured wind was directed downward through shafts that passed over underground water channels called qanats. The air contacted the water, cooled through evaporation, and was discharged into the living space below. The warm air inside the building rose and exited through openings on the opposite side, creating a continuous convection loop. No fan, no electricity, no moving parts at all, just wind, water, and geometry. These systems could drop interior temperatures by up to 18 degrees Fahrenheit below the outside air in the middle of a Persian summer. Archaeologists believe some of these wind catcher systems may date to 4000 BC or earlier, making them potentially 6,000 years old. For context, that is older than the Great Pyramid of Giza, older than Stonehenge, older than written language, and every single one of them operated on the same physics that your sweat glands use right now. When water transitions from a liquid to a vapor, it absorbs energy from its surroundings. That energy is called the latent heat of vaporization. For water, the latent heat is 2,260 joules per gram. That is an enormous amount of energy absorbed per unit of water. Evaporated. When a breeze passes over a wet surface, the water molecules at the surface absorb heat from the moving air, transition into vapor, and carry that thermal energy away with them. The air that continues past the wet surface is measurably cooler because it has donated its heat to the phase change. That is evaporative cooling. It is not a theory. It is not an alternative therapy. It is a thermodynamic law. The same law that makes you feel cold when you step out of a swimming pool on a windy day. The same law that makes a wet towel on your forehead reduce a fever. The same law that makes desert nights cold despite scorching days, because the dry air accelerates evaporation from every surface. And in 1758, Benjamin Franklin proved it experimentally. He and a Cambridge professor named John Hadley used an ether thermometer and a bellows to demonstrate that forced evaporation could drop the temperature of a thermometer bulb to 7 degrees Fahrenheit, well below freezing, on a summer day in Philadelphia. Franklin wrote about the experiment in a letter that same year, concluding that evaporation was a powerful means of producing cold. Franklin documented the principle that powers every swamp cooler ever built. In 1758, 268 years ago. Now here is where the story takes the turn. The HVAC industry does not want you to follow. In 1902, Willis Carrier built the first modern electrical air conditioning unit. It was not designed for comfort. It was designed to solve a humidity problem at a printing company in Brooklyn. The ink was smearing because the paper was absorbing moisture from the hot, humid air. Carrier's machine removed moisture and cooled the air as a side effect. He realized the commercial potential and founded the Carrier Engineering Corporation. By the 1920s, air conditioning had moved from factories into movie theaters, department stores, and government buildings. By the 1950s, residential units began appearing in American homes. And here is where evaporative cooling began, its disappearance from the American consciousness. Evaporative coolers had been widely used across the American Southwest since the early 1900s. They were standard equipment in homes, businesses, and even automobiles. Car-mounted evaporative coolers, called car coolers, were aftermarket accessories that hung on passenger windows from the 1930s through the 1960s. They were cheap, effective, and ran on nothing but water and airflow from the moving vehicle. But evaporative coolers have one limitation that the HVAC industry leveraged into a trillion-dollar business model. They work best in dry climates. In humid environments where the air is already saturated with moisture, the evaporation rate slows and the cooling effect diminishes. This is a real limitation. It is not fabricated. What the industry fabricated was the narrative that because evaporative cooling does not work everywhere, it works nowhere. They marketed refrigerant-based air conditioning as the universal solution. They lobbied for building codes that required mechanical cooling systems meeting specific efficiency ratings that evaporative coolers, being non-compressor devices, could not be categorized under. They convinced an entire generation of homeowners that comfort required a machine that costs $3,000 to $7,000 to install, $150 to $500 per month to operate, and $200 to $500 per year to maintain. And the swamp cooler, which costs $0 to $50 to build, uses 75% less electricity and provides genuine cooling in the climates where most Americans who need cooling actually live, quietly vanished from the conversation. If you have made it this far, you already know more about the physics of cooling than 99% of homeowners and most of the contractors they hire to install $10,000 central air systems. Subscribe and share this with someone who is staring at a $400 electric bill right now and believes there is no alternative. Now stay with me, because the economics of this suppression are staggering. The global HVAC industry generates over $240 billion in annual revenue. In the United States alone, residential air conditioning accounts for roughly $29 billion in annual electricity costs paid by homeowners. The average central air conditioning unit costs between $3,800 and $7,500 installed. A window unit costs $150 to $600. Both require continuous electricity consumption to operate, and that electricity generates a monthly bill that the power company collects for the life of the system. An evaporative cooler uses only a fan and a small water pump. The electricity required to operate both is a fraction of what a compressor-based system demands. Commercial evaporative coolers cost roughly 50% less to install than central AC and consume up to 75% less electricity during operation. Most residential swamp coolers operate at approximately $1 per day in electricity, compared to $3 to $5 per day for comparable air conditioning. Over a 10-year period, the difference in operating cost between a central air system and an evaporative cooler in a suitable climate can exceed $10,000 to $15,000 per household. Multiply that across the roughly 40 million homes in the arid and semi-arid western United States where evaporative cooling is effective, and you begin to see the architecture of the revenue stream that depends on you never building one. You cannot patent evaporative cooling. It is a thermodynamic law. You cannot patent a bucket with a fan and a wet pad. You cannot create a subscription model for water. And you cannot build a $240 billion HVAC empire around a principle that a 5-year-old can demonstrate with a wet towel and a box fan. So the industry did what industries always do. They built the complexity barrier. They made cooling synonymous with compressors and refrigerant and ductwork and annual maintenance contracts and SEER ratings and 10-year warranty packages. They wrapped a simple thermodynamic principle inside a $7,000 machine and convinced you that comfort required financing. Now here is exactly how to build one for $0 to $30 using materials you likely already own. And the design is what professional-grade evaporative coolers use, stripped down to the physics that actually matters. Step 1. Get a 5-gallon plastic bucket with a lid. If you do not have one, any hardware store sells them for under $4. Step 2. Cut 2 to 3 holes, roughly 2 inches in diameter, in the side of the bucket about halfway up. These are your cold air exhaust ports. You can use a hole saw on a drill, a sharp utility knife, or even a heated can. Short sections of PVC pipe inserted into the holes create directional outlets. Step 3. Cut a hole in the center of the lid sized to fit a small desk fan facing downward into the bucket. The fan pushes air down into the interior of the bucket and forces it out through the side exhaust ports. Secure the fan to the lid with screws, zip ties, or silicone adhesive. Step 4. Line the inside of the bucket with an evaporative cooling pad. These are sold at hardware stores for under $10 as replacement pads for commercial swamp coolers. If you do not want to buy a pad, a rolled-up towel, a section of burlap, or even a stack of sponges will work. The material needs to hold water and allow air to pass through it. The more surface area the wet material presents to the moving air, the greater the evaporation rate and the colder the output. Step 5. Add a small submersible pump, the kind sold for tabletop fountains for $5 to $10, connected to a length of aquarium tubing that drips water from the top of the pad. This keeps the pad continuously saturated so the evaporative surface never dries out. Run the pump power line out through a small notch in the bucket rim. Step 6. Fill the bottom of the bucket with water to a level that covers the pump but does not reach the exhaust holes. 2 to 3 inches of water is sufficient for hours of operation. Step 7. Place the lid with the fan on top, plug in the fan and pump, and feel the air coming out of the exhaust ports. On a dry day with outside temperatures above 90 degrees Fahrenheit, the exhaust air will be 10 to 20 degrees cooler than ambient. In the arid Southwest, temperature drops of 20 to 26 degrees have been documented by builders and researchers. For a simpler version requiring even fewer materials, skip the pump and pad entirely. Place frozen water bottles or a gallon jug of ice inside the bucket. Mount the fan on the lid and cut the exhaust holes. The fan forces air over the frozen surface. The ice absorbs heat at 80 calories per gram through the latent heat of fusion, cooling the outgoing air by 10 to 15 degrees in the immediate vicinity. This version is not true evaporative cooling, it is convective cooling over a cold thermal mass, but it works in any humidity level and costs nothing if you already own a fan and a bucket. Total cost for the full evaporative version with pump and pad, under $25. Total cost for the ice version, $0 if you have a fan, a bucket, and a freezer. Total electricity consumption, 10 to 50 watts depending on the fan, roughly 1/10 to 1/20 the consumption of a window air conditioning unit. A camper in southern Arizona documented running a 5-gallon bucket evaporative cooler inside a canvas tent during a July camping trip with daytime temperatures exceeding 105 degrees Fahrenheit. Using a 12-volt fan powered by a small solar panel, the cooler dropped the interior tent temperature from 104 to 82 degrees with no grid electricity at all. Water consumption was approximately 1 gallon every 2 hours. Total operational cost, $0. I need to be completely honest with you about limitations. Evaporative cooling works best when humidity is below 50%. In the southeastern United States, the Gulf Coast, and other humid regions, the air is already carrying so much moisture that additional evaporation slows dramatically. In these climates, the temperature drop may only be 5 to 8 degrees, which is noticeable but not transformative. If you live in Houston, Miami, Atlanta, or anywhere with summer humidity regularly above 60%, evaporative cooling alone will not replace your air conditioner. However, even in moderate humidity, an evaporative cooler used in conjunction with existing AC can reduce the load on your compressor significantly. Running the swamp cooler to pre-cool incoming air before it reaches the AC unit means the compressor cycles less frequently, which directly reduces electricity consumption and extends the life of the equipment. The ice-based version works in any humidity, but requires a supply of frozen bottles or jugs, which means your freezer is consuming electricity to make the ice. For truly off-grid applications, this is a limitation. For grid-connected homes, the electricity used by the freezer is still dramatically less than running an AC compressor. Keep the bucket clean. Standing water breeds mosquitoes and bacteria. Change the water daily. Add a capful of hydrogen peroxide if the water sits for extended periods. Clean the pad or replace it if mold develops. This knowledge never disappeared. It was outspent. The ancient Egyptians cooled their homes with wet reeds in doorways 4,500 years ago. Persian engineers built windcatcher towers over underground water channels that dropped interior temperatures by 18 degrees without a single moving part. Benjamin Franklin proved the thermodynamics in a Philadelphia laboratory in 1758. American homeowners across the Southwest cooled their houses with swamp coolers for decades before the HVAC industry convinced them to replace a $50 device with a $7,000 machine. A $240 billion HVAC industry depends on you believing that cool air requires a compressor. A $29 billion annual electricity bill for residential AC depends on you never questioning whether a fan and water could do the same job for a fraction of the cost. And every contractor who quotes you $8,000 for a new central air system depends on you never looking up from the estimate long enough to remember that the Egyptians solved this problem with a clay pot and a breeze. But now you know, and the physics are too old, too proven, and too simple to be erased again. That room you have been avoiding all summer because the AC cannot keep up could be comfortable tonight. That electric bill you have been dreading could drop by half next month. That off-grid campsite, that van, that workshop, that garage, that greenhouse, that chicken coop, every enclosed space you have ever wished was cooler could be 20 degrees colder by this weekend for the cost of a bucket of water and an afternoon of your time. The air was never the enemy. The bill was. And the bill only exists because someone convinced you that the only way to move heat was with a machine that runs on their electricity. Water has been moving heat for 4,500 years. It does not need a plug, and it has never sent anyone an invoice. If this vault changed how you think about the thermostat in your house, subscribe and share this video right now. Every share puts this knowledge in front of someone the power company was counting on never finding it. Every subscription keeps this channel digging deeper into the vaults they thought were sealed forever.